Okay, so I am delighted to introduce today's speaker, Marv Geller. For those of you who don't know Marv, for those of you who know Marv, I feel that I really don't have to say too much. Marv was here for many years. He was founding director of ITPA. He was recruited by Jerry Schugel. He served as dean for SoMAS for several years. He is a fellow of AMS, a fellow of ATU. He's quite the scientist, and he's been acknowledged as such, and he has a long, prolific career. He's graduated a lot of students who've gone on to do great things, blah, 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 right? So, but what I actually thought would be really interesting is I want to take you back to 1969, which is when Marv defended his PhD thesis. And the title of his thesis was something about lunar tides. And on page 172, I quote, "The value of the Newtonian cooling coefficient depends critically on the assumed ozone photochemistry, and this photochemistry is still undetermined. It was mentioned earlier that calculations in this study suggest that the classical ozone photochemistry is not correct. Perhaps the weight of evidence from similar theoretical calculations of ozone Newtonian cooling will serve to settle the question of ozone photochemistry to some extent." Now I can take it back to 1969. We knew about the Chapman cycle, and I know all of you know about the Chapman cycle, but we didn't understand ozone photochemistry. And in fact, in 1970, a guy named Paul Crutzen wrote a paper talking about the catalytic destruction of ozone by NO and NO2. And this was followed up in 1979 by his paper that basically led to his awarding of the Nobel Prize. And of course, Sherry Rowland, Mario Molina's work followed Paul's work on the destruction of stratospheric ozone with halogen chemistry. And this was before the observation of the stratospheric ozone hole over Antarctica in 1980, which was published in 1985. So this is a fantastic example of a then graduate student understanding not only what he's talking about in his thesis, which is dynamics, but he has to think about radiation, and he has to think about chemistry. This is one of the reasons why the faculty here really try to give the students this fundamental understanding in all disciplines. Atmospheric sciences is a science of many different specialties, but that doesn't mean just because you're a dynamicist, you get a pass on not knowing chemistry. Marv knows more chemistry than some atmospheric chemists I know. So I think this really speaks, not in this room, this really speaks though to the kind of depth and breadth that really good scientists have. And it's, you know, to go back to a thesis that's literally a half century old, not that I'm dating you or anything. And by the way, I don't remember if your thesis was correct in which direction of the ozone prediction, but it's remarkable, I think, that he's considering chemistry in a dynamics PhD thesis. And this kind of leads to his contributions to the field in general, which were never limited just to dynamics throughout his career as NASA branch chief, as professor at the University of Illinois, Rosenstiel, as well as Stony Brook. Marv just got a new NSF award. I think it was probably processed this month from the National Science Foundation. And he's going to talk to us a little bit about unstable layers. I don't even know where, high up, down low, everywhere?
Everywhere.
Everywhere.
They're all around.
Marv, they're all wrong.
Actually, John, when you talk about the ozone business, I did have the advantage of seeing a paper by Benson and Axworthy at that point in time, which showed that the Chapman reactions are not sufficient to explain the observation of the ozone level. So I did have that advantage. Okay, well, first of all, it's great to be here. It's sort of like a reunion, and seeing all these youngish faculty members that came here when they were children, and now they're your senior professors. What does that say I am? So anyhow, so the nature of this talk is this business on unstable layers, and I'll talk about is referring to work that I've sort of done, and it appeared in a recent paper, Monthly Weather Review. And then this part is ongoing research. And let me say something to the students and to the faculty here. When I left Stony Brook, I used to do most of our research with graduate students. But when I left Stony Brook, I didn't have graduate students anymore. So my colleagues became my past PhD students. Some of my PhD students, past PhD students are in the mid-70s, so another issue. So, but the moral is that faculty members should be nice to their students, because in the future, they may interact with them in important manners. And the students should be nice to their faculty advisors for the same reason. So, there's some issues. Anyhow, first thing, given the fact that SoMAS does fundamental science and applications, I thought the first thing I should mention is why would anyone study this stuff? And so basically, unstable layers in the atmosphere, first of all, result from convection. We know that. That's unstable. Shear, how we come with numbers and stability. And even if you have turbulence itself, it can move the density around where you'll have less dense air over more dense air, and that will give you an unstable layer. The other issue, and I'll talk about this a little bit later, is identification of the unstable layers as a starting point for Thorpe analysis of turbulence. And that's also nice because here I am in a School of Marine and Atmospheric Science. And actually the Thorpe analysis was originated by an oceanographer doing research in a Scottish loch. So that's kind of interesting. We're applying it to the atmosphere. And lastly, turbulence is important for civil aviation. Remember when we used to fly? So it can interfere with optical remote sensing. And also within the atmosphere, away from the boundary layer, that's how kinetic energy is dissipated. So it's not just doing crossword puzzles, although that's okay too. So what I'm going to talk about is a brief summary of the Thorpe method. There's a recent paper in Monthly Weather Review on climatology of unstable layers. We'll talk about a bit. And then some preliminary results of ongoing research, showing you how preliminary. While I was in the car driving here, I kept getting updated figures from a colleague of mine. So it's truly ongoing research. And then some future plans. Okay, Thorpe method. In the atmosphere, we can think sort of potential temperature, theta, plays the role of density in the ocean, basically. And so as you go up in altitude, a stable layer is when the potential temperature increases. Just like in the ocean, it's stable when the density decreases. Okay, so this red line might indicate an atmospheric sounding where we derive potential temperature from pressure, temperature measurements, and humidity. And so what the Thorpe does is it takes this profile and you resort the profile where you make it monotonic. So we shift this up to here, and we end up with a profile that looks like the blue profile, which is now stable. And then we keep track of all the displacements between Z and VS. So for example, up here, you see the displacement is around 700 meters, which is roughly there. And then as we go down, displacements are less and less. And then these fluctuations here are these little fluctuations there, which indicate little unstable layers. Now, you have to quality control this because this is using raw radiosonde data. So we're getting something every second, which is about 5 meters at a balloon rise rate. And so you've got noise in this profile. So you do statistical analyses to try to eliminate, make sure you're not looking at the instability characteristics of noise. You don't want to do that. So this is from a paper by Ko et al., who's a student of Professor Chun. I'll go on with this paper. So because it was co-author, I had to actually study what this figure was because okay. So anyhow, that's a Thorpe method. The Thorpe method is you do this sorting, you assemble DZ, and so on the next slide you'll see the sum of DZs, And of course, displacements are symmetric in the end, so it has to, at the end, come back to 0. And so this is the cumulative disease. And then the key is you take the root mean square of these Thorpe displacements and you derive something called a Thorpe scale. And the Thorpe scale would be a characteristic of the entire unstable layer. So in this case, the Thorpe scale would be 370 meters. Okay. And then there's a key. The Thorpe scale is interesting, but it doesn't have a lot to do with turbulence. It probably is more of an indication of the eddy sizes of the overturning, to be honest with you. But what it does have is something called the Osmondome scale, which I go into. But it's the largest scale where you don't have to worry, where largest scale before stratification becomes important to the treatment of turbulence. So you assume that the linear relationship, and that's a questionable assumption, by the way, because you're looking at a sounding, you have no idea of the physics from which the unstable layer arose or turbulence arose. You have no idea what's initial stages, late stage turbulence, or even whether turbulence has a start at all, for example. So it probably has something to do in a statistical manner, but each individual layer is very, very questionable. But Karor theory says that it's related to the dissipation rate of turbulent kinetic energy epsilon over the Brock-Weissler frequency G. That's a Karor theory. So, and then you do a little arithmetic, and knowing the Thorpe scale, knowing the Brock-Weissler frequency, knowing the C, you can derive the dissipation rate of turbulent kinetic energy. That's the idea of the Thorpe. But the beginning part is identification of the unstable layers. So we went way back in this paper and looked at the characteristics of the unstable layers. This is just some random place, Riverton, Wyoming. And if you look at it, and this is a plot of the, basically the frequency per sounding of a turbulent layer of this thickness as a function of altitude. See what it's plotting there? So it's turbulent layer thickness, altitude, and the color scale is the frequency of the currents of these layers. So first thing you see that's quite obvious is in the troposphere, there's more thick layers than the stratosphere, because the troposphere is less stable than the stratosphere. But then you can look a little further and you'll see some other stuff. So here's what I just said. There are thicker layers in the troposphere and stratosphere. But if you look a little more closely, December's down here. This is over an 11-year period. There look to be more stratospheric layers, unstable layers, December than July. See up here? There's just more in that end. That's kind of interesting. What's really interesting is there seem to be more unstable layers at midnight universal time than at noon universal time. Look at July, and you see there's a greater density of these layers, and you see this is thicker, the green extends further. There just seem to be more unstable layers at universal time midnight than universal time noon. And it's particularly notable in July. Okay. Also true in December, but to a lesser extent. And so, in fact, we can plot a bunch of other stuff. Where now we're plotting the aggregate frequency. So we take the aggregate frequency of unstable layers 10 to 400 meters between an altitude of 50 and 25 kilometers lower stratosphere. And we plot them. And you see, sure enough, the blue curve is 0, 0, Z, or midnight. And the red curve is noon. And there's a very clear difference in the occurrence of these unstable layers in the stratosphere. Furthermore, if you look here at 0, 0, Z, this is the unstable layer as a function of altitude. You see much more penetration into higher layers, and the thicker layers you see. And basically, this one is the most important. Okay. But here's another station, Greensboro. It's a little lower latitude. Same plot, same type of plot. But it's greater at noon universal time than at midnight universal time. So one question occurs: why? Why would that be the case? And when you get for the students in particular, when you have a why like this, you write a research grant application, which I did, and that's the one that just got funded. Okay, so the why we haven't quite answered yet. I'll talk about how we'll talk about it. Well, if we explore it further, there's obviously limitations. If we look at diurnal cycles, one of the limitations is radiosondes about twice a day. We don't know what happens in between. So that's it. And also, of course, they're at discrete locations. But if we now plot the geographic distribution of multi-year average, that aggregate frequency, the one, this stuff, if we plot that for December, I'd almost call them the meteorological seasons. December, January, February, March, April, May, June, July, August, September, October. This is Riverton, Wyoming, the circle. And this is Greensboro, North Carolina down here. You see that there's a pattern here. That if you look at 0, 0, Z, let's look at July because it's the most obvious. If you look here, we're in the blue area here. But if you look down, we're in the green area. And it's true in all seasons. So there appears to be a geographical pattern where the time of maximum unstable layers in the stratosphere is different in the eastern US than in the western US, which is kind of interesting. Those are two mid-latitude stations. What about a tropical station? So this is Karor. Karor is right near the equator. The next plot will show its exact location. Same layer frequency as a function of thickness, altitude. And we see a number of things. We see more unstable layers at 0, 0, Z than at 12. Let's see a little bit more. It's more obvious. Okay. But the most interesting thing is this notch. See, in all these plots, there's kind of a hole in thin layers, but a lot of thicker layers at about 12 kilometers. That it's quite striking. If we do the same plot of aggregate frequency for Karor, now we're actually going to tell you where it is. It's about 7.3 north. Again, more lower stratosphere, unstable layers at 0 Z to 12 Z, just like I told you. But what about the notch? What about the notch? Well, it pays to have friends. I asked a friend of mine, actually, do you know Todd Lane in Australia? No. I asked Todd Lane, I asked him if this rang a bell of what's going on 12 kilometers. He said, well, you should look at this paper by Grimes. So, another message, have friends. So, Grimes et al. Had written this 2010 paper Journal of Climate, where they used GPS temperature profiles and looked at the climatology of atmospheric static stability. And they found this stability minimum at a height of around 12 kilometers in the tropics. Okay, so this one, I was just reading, I forgot what the figure was. This is in conventional coordinates. This is in Tropopause average coordinates. You Tropopause average because the Tropopause average days, if you want to distribute. They look rather similar. But so in that paper, they refer to a couple of other papers, and they've identified this stability minimum with cloud top outflow in the tropics. So this is from Gettleman and Forster, 2002. And there's high convection, there's low convection. The routine run-of-the-mill convection, you tend to have identified this minimum lapse rate, which would be that stability, where you'd have outflow from the more ubiquitous convective elements in the tropics. So perhaps this notch might be a manifestation of you've got turbulence up at the top of the cloud and you're blowing it off. And if you're blowing turbulence off, you might have the turbulent large eddies just obliterating the small eddies by just mixing them up. That seems to be feasible. Or there might be something else going on, and that is radiosondes go up in cloud, outside cloud. You're also mixing this up with what's going on within the cloud themselves. Another question, which means you should write a proposal. So
what is the elevation of commercial aircraft fly at 12? Isn't it?
this is at the upper end of commercial aircraft going over the tropics, about I think I figured it was about 38,000 feet. So this has some practical implications also for long distance aircraft. Good point. Now, we did notice a data problem. I'm not sure if you might have seen this before, Brian, or not. But we looked at these statistics. Again, this aggregate frequency plot I've shown you before. But look at this. This doesn't look real, does it? Well, we did a little research, and that's the time that they transitioned from Lockheed Martin radiosonde instruments to the Weissler. So, and in the analysis of the climatology, we saw a bunch of stations like that. And we actually have a table of the stations that suffer from a similar data defect. One of the reviewers, when he submitted the paper, said, well, why is that? Another proposal. Okay. So, okay.
How do you know which one is correct? They can't be both correct.
They cannot be both correct.
Or they can be both wrong.
So we threw all the stations like that out of the climatology because of that very reason.
Yeah, but then your other stations, they have to have one or the other type of.
Right, so I could have changed the title to a study, a climatology of atmospheric unstable layers using the Lockheed Mark II. Yeah, you're right, I could have titled it that way. If I wanted. So, but it's something to look out for when you're dealing with real data, particularly what's going on. Incidentally, there's a lot of things in meteorology to look out for. When I was here, I was asked to serve on an academic fraud investigation committee at the university. And I was honored as the atmospheric scientist, not from that institution. There was an engineer from the institution. There was a biologist from the institution. And in that paper, they had stated that they threw out data from stations in China, which did not have significant changes in population or changes in instrumentation. I dare say there are no such stations probably in China. So, so the thing was thrown out because, but, basically you've got to look out when you deal with data, change in instrumentation, change in the environment. So real data theory is much clearer. Anyhow, so that's a summary of the climatology of unstable layers. Changing gears completely. Different studies have found differences. And by the way, this is the unstable layers I've written actually 3 grants since I retired from Stony Brook. The first subject was the first grant. This is the second grant that we're working on now. The third grant just got funded is trying to explain the why of the first unstable layer. So different studies have found differences now through the maximum turbulence. Okay. So what do we got here? We've got different seasons. So this would be summer, and you see what you've got here, the left panel is this Karor paper. So that's using Thorpe analysis. And this is the height of tropopause during the season. So here's the summer season. The turbulence maximized below it, green below it, blue below it. So the turbulence is maximizing slightly below the tropopause. Here's another paper by Mason and Eaton. And here they're using radar determinations of turbulence. And you have to learn a little about a lot of things that we research on. In radar, if you look at fluctuations of vertical velocity, there's an empirical formula that you can use to relate to the turbulence, intensity of turbulence. So that's the do here. And this is tropopause average. Each time you get a sounding, where's the tropopause? You assign that height 0 and plot everything with respect to the height of tropopause. And you see for the different seasons, it's maximizing at or above the tropopause. So what's going on here? Now I should say at this point, this is from a selection of, I think, 68 US stations. So it covers sort of the continental US latitude range. This is from white sands in Mexico. So why? Well, one was radar, one was Thorpe analysis. But here's a paper by Coma et al. And Coma et al., this left figure is the radar measurements, and B is from Thorpe analysis. And you see the maxima appears to be above the tropopause. There are some differences, but both appear to be above the tropopause. So while there are differences in the radar and the Thorpe, which is another subject to investigate, that does not seem to be confidence. But one thing that might is show a station that basically is an Antarctic station. And so it could be quite different from white sands or other stations. Now, there are some clues. In this Coe et al. Paper, they did sort of this scatter plot type thing of shear versus turbulence, front Weissler frequency versus turbulence for the troposphere and the stratosphere. In the troposphere, there's more turbulence for lower stability. For lower stability, as you'd expect in a convective environment. Not too much relation to shear, to be honest with you, much more of an n squared. But in the stratosphere, it's the opposite. There's more turbulence with greater stability. Well, why might that be the case? Well, I've done research. You name the waves, I'll look at the atmosphere. So this is the dispersion relation for inertia gravity waves. This is vertical wave number, horizontal wave number squared, and squared, intrinsic frequency, Coriolis, scale height. And cut to the crap a little bit, the medium frequency, same thing's true with this. You see that m squared goes as n squared over omega squared, because for waves that have the intrinsic frequency greater than Brook-Weisler, which is a lot of waves, it'll go like this. So you see that m squared, the vertical wave number, kind of increases with Brook-Weisler frequency. And if the vertical wave number increases, the vertical wavelength decreases, which will give you more chance for gravity waves to break, like ocean waves. Okay. So if you have inertia gravity waves propagating upward, where is a region where n squared increases? Tropopause. You go from the troposphere to the stratosphere. Well, paper by Tom Berner, JGR, and he's got 3 different stations at 33, 40, 48, 60. It's the temperature profiles, higher tropopause, lower latitude. And these are all tropopause averaged. Each sounding, you take the tropopause and key everything. Higher tropopause. But when you calculate the Brook-Weisler frequency of each of these, it has a really interesting shape. It's low in the troposphere, starts increasing on the upper troposphere. Sharp change right near the tropopause, and then decreases back to its stratospheric level. Well, this structure is very different from that structure. And if you have gravity waves, atmospheric gravity waves propagating into these different environments, we might find that they'll break very differently. And so that leads us to the hypothesis that, let's operate the hypothesis that turbulence in tropopause is primarily caused by gravity wave breaking, away from the jet stream, but by gravity wave breaking. So, well, I visit arbitrary stations. I just picked up the same ones we looked at before, Riverton and Greensboro. And would plot, remember, from LT and N squared, we can derive the dissipation rate of turbulent kinetic energy. And this is a plot of that for both stations. And this is the tropopause, higher in summer. And you see that the turbulence here maximum extent as well at the tropopause, but quite a bit below the tropopause too. Greensboro, maybe a little less below the tropopause. Well, we can answer that question by doing tropopause average results for those 2 stations. And then it becomes an average. So 0 is the height of the average tropopause, and you see that the maximum turbulence intensity is occurring at or below the tropopause. Here, it looks like maybe similar, because these stations are pretty close in latitude. If we start looking at the greater variety, you can't do this. So I will read it for you. This is Ponape, right near the equator. This is San Juan, Puerto Rico. So this would be at about 0 to 10. This would be 10 to 20. And this would be Miami, 20 to 30. Greensboro, 30 to 40. This is Alexandria, something. They're higher latitude, higher latitude. And you see a very big difference. In the tropics, turbulence once occurring all over the place, but it's sort of at the tropopause. As we go to higher latitudes. It's tough to see the tropopause here. It's appearing all below the tropopause. Again, the tropopause average, and it becomes more apparent. This would be the tropical one. Now it's clear that the maximum is below the tropopause. But as we go to higher latitude, it's kind of a bit higher than the tropopause. And in Fairbanks, Alaska, if anything, it's maximizing a little above the tropopause. So this is a paper I have to sit down and write. Draw this one. Okay, so this one just kill a dead horse. Let's make sure it's really dead. Okay, so if we then ban these 5 stations that occur between 0 and 10, and we ban these 15 between 42 and 47, then we get average situations for latitude bands instead of looking at discrete stations. And again, sort of at the tropopause, a little lower down, looks like below the tropopause, and up higher, more above the tropopause. So it looks like the latitude where we're doing it is important. We would hypothesize it's because of the different tropopause structures at different latitudes. I can even do more, and now we're averaging bands again, but it's plotted differently. Now it's plotted tropopause averaged. And here we see something interesting. At low latitudes, seasons don't count that much here. But what's interesting is what goes from tropics to the extratropics, we see a difference in shape. We see this maximum occurring below the tropopause, but not for all seasons. This is a glitch we haven't figured out yet. But you see this maximum as you go higher and higher, it's occurring from below the tropopause to more or less at the tropopause. But what complicates the matter is when you look at stations like this, the shape in January, July, June, July, August, September, October, November, these look more like the tropics, and these look more like mid-latitudes, which makes sense because as the year progresses, so it's a function of latitude and season, and they're mixed up with one another at middle latitudes. So that's what I'm going to try to explain. Okay, so I'm actually getting through fairly quickly. It's okay. So summarizing a little bit, we looked at analysis of unstable layers using US Radiosonde data. By the way, recently, this is something your students may be interested in or wherever, but actually, if you look at the Spark newsletter, there's some announcements by me that worldwide, there's more worldwide availability of raw radiosonde data, and which is being enabled by a collaboration between ECMWF and NCEI. Okay. And then it shows how to access them. So now what we did with US data is now available elsewhere. So it gives a local time too. The new proposal, the one that Stony Brook has been awarded to Stony Brook, is what we propose to do is look at instances of gravity wave breaking and ray trace the waves back to their source and see if there's a difference in behavior of the source of the gravity waves that led to the breaking and the turbulence in eastern and western US. it's entirely possible, like we've done some previous work, where as you look at the jet, there's sort of a curvature in the west, which is favorable for launching gravity waves. And so it might be very different to the east. And also one could be convective, one could be shear. All these things.
When you say the west, you mean the Rockies or?
Well, it looked like, when I looked at that plot, it looked like it's not, it looks like eastern, cut the US in half, and it looks like this pretty much on that geographic distribution. You can't identify with the Rockies. It's not over the Rockies, not over the Rockies. I don't know. So we're seeing if different gravity wave sources for the continent. This notch we saw at Karor, new proposal, we'll see if such a notch is present in other near equatorial stations. Frankly speaking, could have done that already, but that's prejudice against doing work for free. So, okay, so that's in the new proposal. Okay, so to see if such a notch is present in those near equatorial. And if you look at the stability maximum, it moves in latitude seasonally. And we'll see if that notch shows a similar morphology as to the minimum. See if we can identify it with that feature. We will also examine with respect to cloud, look at cloud remote sensing, in cloud, out cloud, downflow, and see if we can identify it with that cloud outflow. Low up turbulence. We'll also do some modeling studies to see if different gravity wave breaking, the different tropopause structures might account for what we showed you there. Now, this is some highly technical issues. My colleagues, Dave Fritz, Lin Wang, do very, very detailed numerical simulations of turbulence, but to simulate the turbulence scales, you have to have very, very high resolution because you have to correctly simulate that part of the inertia spectrum that goes down to the dissipation range of viscosity. And that gets very, very expensive. Now, for high Reynolds number regions like the stratosphere, the requirements are even beyond theirs. So we'll look at not the turbulence that results from gravity wave breaking, but look at the gravity wave breaking itself, that we don't need such high resolution to do.
So what is that wave number in the atmosphere in terms of the dissipation? Because in the ocean it's about a centimeter.
I think it's in the order of, I don't know, it's a quick answer, but I'd say it would be more like, does anyone want to answer that? I'd say neither, maybe a little less. Something too small to do their simulations. Yeah. Okay. Now, there's something I haven't talked about at all here, but I find rather interesting, and it applies to the ocean and the atmosphere too. If you have a stable medium where sporadically turbulent layers appear, disappear, then mixing can take place quite efficiently within the turbulent layers, but inefficiently between the turbulent layers and the stable region. So if you've got that sort of an environment, what is the effective mixing in that region in which there are sporadically appearing and disappearing turbulent layers? This has been a subject that you want, figure names, they've done. So we want to look at that also. And see, for example, how bad a mistake you're making if you're just being dumb. But for instance, if you get the turbulence and you get these layers, 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 and you just arithmetically average and get the mean turbulence mixing, how much of a mistake are you making versus doing that versus finding the effective mixing using this one? It's another aspect. And I think that's it. So that's how I've spent my retirement. Okay. Thank you.